Okay. So reflection with normal incidence, guys. I just want you to be able to recognize this formula. Please don't ask me for no math problems. I'm not giving them to you. I'm not giving them to you. I just want you to be able to recognize that this formula is the intensity reflection coefficient formula. Okay? Looks familiar in the book? Looks familiar in the book? Okay? Recognize that is what it is. Okay? That's all I want you to do. I don't want you to have to try to figure no math out. I'm not going to make you work out this formula. I'm not going to give you Z1, Z2. I'm not going to ask you for none of that.
But what is Z1 and Z2?
Z2, that's the medium 2. Z1, that's medium 1. So if we're looking at this right here, Z2, medium 2. Z1, medium 1. I'm not going to ask you none of that though. I'm not going to ask you none of that. Remember, what is Z anyway?
Zone.
What is Z anyway?
Zone?
No, that's the impedance.
No.
It's impedance, right? It's the symbol for impedance. Remember, the units of impedance are rails, usually represented by the letter Z. Okay?
Impedance or impedance?
All right. So, again, guys, just recognize this formula when you see it. You're not going to have any math on this. So just recognize this part right here. When you see that, just be able to recognize that that is the intensity reflection coefficient formula. All right? So, the intensity transmission coefficient is the percentage of the intensity that continues to move forward when the beam reaches a boundary between two media. With normal incidence, all of the sound is transmitted when the media have the same impedance, correct? Okay, remember, like I said, we won't get a reflection if the mediums have identical impedance. That means all of that sound is being transmitted if we're not getting a reflection, right? Because we're not losing energy. We have to account for that energy. All right?
Well, it means there's no resistance. So
Exactly. It's going to keep transmitting. It's going to keep transmitting. Again, guys, just recognize the formula. That's all I want from you. Somebody write that down. Recognize the formula. That's it. That's it. That's all I want you to do. Recognize the formula for that. IRC, Z2 minus Z1 over Z1, Z2 plus Z1 squared. That's for the IRC. That's, yeah, look at the percentage. Yes, ma'am. Yes, ma'am. So, ITC is two formulas that give you transmitted intensity over incident intensity, or 1 minus the intensity reflection coefficient. That makes sense, right? Because 1, remember, we're talking about 1, that's going to be our total intensity, right? Right? That's our 1, our 100. So if we minus the intensity reflection coefficient, of course we're going to get the transmission coefficient, right? Right? Because all of that energy must be accounted for. All right? Again, guys, no math on this. Just recognize those.
And that's called a transmission coefficient?
Correct. In percentages. Remember, our coefficients, ITC and IRC, are in percentages. Okay? Just recognize those formulas, guys. Circle them, do what you got to do. Put them to memory. Recognize those formulas. All right? So, let's talk about reflection and transmission. Any questions about about normal incidence? Remember, normal incidence has everything to do with the difference between impedance values. Okay? But we won't get a reflection if the impedances are the same. If the impedances are very different, we're going to get a nice strong reflection. Okay? When we're hitting something at normal incidence. Okay? Normal incidence is all about impedance differences. Okay? That's a quick way to remember that. Normal incidence is all about impedance differences. Right? So now we're going to talk about reflection and transmission with oblique incidence. Oblique incidence. Okay? So, like I just said, with normal incidence, the study of reflection and transmission when sound strikes the interface depends on the impedance difference. Right? Normal incidence, 90 degrees. Okay? When we talk about oblique incidence, guys, it is impossible to predict whether sound will reflect or transmit after striking a boundary obliquely. All caps, that's why I'm yelling. All right? It's impossible to predict that. All right? They cannot put a number on that. All Alright? It's too complex. Alright? It's too complex to figure that out. That's all you need to know. Don't ask me why it's so complex. Just know that it's too complex. Alright? It is impossible to predict whether sound will transmit or reflect with oblique incidence. Question mark, we don't know. Alright? With oblique incidence, reflections may or may not occur, even when the impedances of the two media are identical. Just the opposites. Reflections may or may not occur, even when the impedance are very different. Okay? Therefore, the physics of reflection and transmission with oblique incidence is entirely unrelated with that of normal incidence. Why is that, Samin?
Say it again. Sorry, I was nooding.
Why is the physics of reflection and transmission with oblique incidence is entirely unrelated with normal incidence?
Because of
Because normal incidence depends on the impedance differences between the mediums, right? Alright? Normal incidence depends on the impedance differences. We can't predict whether sound is going to transmit or reflect with oblique incidence. Alright? We're talking about the IRC and ITC, we're talking about normal incidence. Alright? Oblique incidence again, guys. When sound beams strike the boundary obliquely, reflection may or may not occur. Okay? We can't predict that. The presence of reflection is hard to predict, but there are two principles that will always apply to reflection with oblique incidence. That is the conservation of energy. Okay? Again, sound, the energy has to go somewhere, right? It's either going to transmit or it's going to reflect. We know this because that's just the physics of how physics works. Alright? And also, we know that the reflection angle equals the incident angle. Whatever angle we're hitting the boundary at, that's going to be the equivalent of the, whatever the incident angle is coming out of the transducer, the reflection angle is going to be equivalent to that. Okay? So if we're hitting something obliquely like this, what kind of reflection is this, guys? What kind of reflection? Not incidence.
Spatial.
Acute.
Reflection, not incidence. What are two reflections, guys? Two reflections. Specular and diffuse, right? Look at this boundary. What's up with this boundary? Isn't that smooth?
Yes.
Yeah.
So that's specular.
What kind is that?
Specular.
Specular reflection. Remember, when it's specular reflection, we're not going to get, that sound's not going to come back to the transducer, right?
It's gonna scatter. Or go different
No, it's going to go in a different direction.
Yeah.
It's going to go in a different direction. Okay? Diffuse reflection, it may scatter or come back with less intensity. That's the disadvantage, is that we're not going to get strong echoes back. Okay? Be careful what I'm asking for. If I'm asking for incidence, then I'm talking about whether it's 90 degrees or it's oblique. This would be oblique incidence. I'm asking you what kind of reflection is that? But you can just look at the boundary and see that that's specular reflection because that boundary is smooth. Okay? So know these two principles, guys. These two principles always apply when we're talking about reflection with oblique incidence.
When we talk about conservation of energy, what are they saying?
We're saying that energy is neither created nor destroyed.
Okay.
We know that even though we can't predict how that if the sound is going to transmit or if it's going to reflect, we know that that energy has to be accounted for and it's either going to transmit or reflect. The amount, we can't predict that. Okay? That's what that's saying. That's all that's saying, is that the energy has to be accounted for. The energy is not just going to poof and disappear. Okay? That's why we still get some sound back. Like I said, this beam, ultrasound beams, guys, just don't come out in straight lines. Like it travels in straight lines, of course, but the beam, the center of the beam, it may come out straight. But the beam the sides of the beam, they may come out at angles. There's a such thing as called beam steering. So even though it looks like it's straight, this one transducer is going to send out multiple beams. Get my marker. So that's how we're able to cover, that's how we're able to not, it's overlapping. That's how we're able not to miss any spaces. So we got our transducer again, guys. Don't laugh at my transducer. So initially, we're going to send a beam out. That's one beam. We're going to send a beam out like this, and it's gonna send a beam out like this. That's how it has that overlap. Okay, that's called beam steering. All right. So don't just think that single every time you see an ultrasound, because I know this image is just for illustration purposes, right? But when the actual sound beam comes out, it doesn't come out in a straight line like that. It's fans. It's boom, 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 boom across that beam. It just keeps doing this the whole time. Just keeps fanning. That's how we're able to see. Think about how we're able to see. We're pointing directly at the aorta, right? But if you're skinny enough, I know we can see the president. We can see her kidneys too, right? That's because that beam is fanning out this way. And it's showing that way. Then it's showing the middle. Then it's showing the side. Remember how fast it's happening? Of course, we can't see that happening in our time because we can't see that fast. And that's how fast sound is moving. Okay? But that's what's happening. All right? I don't want this illustration to make you think that, oh, just one beam comes out of there and that's it. It don't work like that to get our images.
It's I thought it depends on the probe, like if it's curvilinear or it is linear. If it's curvilinear, because we know it's already curved, it's gonna spread.
Even if it's a linear probe, it's still gonna be the same. Even if say that's a curvilinear probe right there, right? So this is my linear probe. It's still gonna straight line, and it's still gonna go like that. It's called beam steering. Okay? It's still gonna go all of those directions. That's how you're able to see so wide. I don't know if you guys ever use the if you ever use the linear transducer like the 12. That's why you can use wide scan on that, right? Because the beam can actually point into the direction it needs to point. That's why you have the widescreen function. All right. Okay. So the conservation of energy must be applied with oblique incidence. The sum of the percentage of the sound reflected and the percentage of the sound transmitted must equal 100. Of course. Okay? So 100 equals the reflection coefficient and the transmission coefficient.
It's not the future. النظارة بتاعت الأطفال. النظارة بتاعت الأطفال.
I got it. So, again, conservation of energy, that just means that all of the energy must be accounted for. We're not losing energy here. So, even though the incident beam is sending out a certain intensity, we know that we can't predict how much is going to be reflected or transmitted, but we know that 100% is going to be either reflected and transmitted, right? That's all that's saying. You're not losing any of that energy. Okay? So 100% equals the reflection coefficient plus the transmission coefficient, and the incident intensity equals the reflected intensity plus the transmitted intensity. Okay? But I can't put numbers to that, right? Because we can't predict those numbers. Okay? I can't predict that percentage. All right? But I just want, that's what the conservation of energy means, that all of the energy, 100% of the energy must be accounted for. All right? This is the image they have in the book right there. When the sound beam strikes a boundary at oblique incidence, the reflection angle equals the incident angle. Here goes our boundary right there. Here's our initial beam right here, hitting our medium. The reflected angle is going to equal this angle right here. All right. Also, there is conservation of energy, meaning that this reflected intensity and this transmitted intensity are going to equal that initial intensity. Same thing, right? Okay. Whatever percentage is transmitted, whatever percentage is reflected, are going to equal 100%. Okay? Because all of this energy has to be accounted for. That's all that means. I don't want you. I just want you to know what conservation of energy means. Energy neither destroyed or lost. All right. And also, the reflection angle equals the incident angle. Thank you, ma'am. Okay. When the reflection occurs, with oblique incidence, the sound beam is not directed back towards the transducer. Again, what kind of reflection is this, guys?
Oblique.
Reflection.
Oh,
The specular reflection, right? This is a smooth boundary right here, right?